Okay, welcome everyone to today's lecture recap. And as I mentioned last time, we're going to be starting a completely new topic today. That's the topic of oscillations and waves. And so just to kind of connect it with what we have been talking about, thermodynamics had to do with the random microscopic motions of molecules in a solid or a liquid or a gas. And now we're going to move on to the situation where we have collective motions of these molecules, so large groups of molecules that are moving together. And so this is the topic of oscillations and waves. So if you have a vibration in a solid, or a wave traveling through a solid, or a liquid, or a gas, then you have still these random microscopic motions of the molecules. But then on top of that, you also have some collective motions where many of the molecules have sort of velocities that are correlated with each other. And so we're going to start out just understanding what is the basic physics that gives rise to these sorts of oscillations. And to do that, I'll actually talk about an example that should be familiar to everyone. So this is just the same kind of thing that we've been discussing. You can imagine a gas in a cylinder, and here there's a piston. And we first imagine that the piston it's freely movable, but it's in some equilibrium configuration. And so what we mean by that, by the idea of mechanical equilibrium, is just the situation where the net force, in this case on our piston, is equal to 0. And in this case, that's coming from a number of different individual forces. So you have the force from the gas inside the cylinder, you have the force from the air above the piston, and you have the force of gravity on the piston. And all of those should add to 0 in the situation where the piston is at its equilibrium height. So next we want to think about what happens if I were to perturb that system away from the equilibrium configuration. So take a moment to imagine that I now go in and move the piston down. Maybe I just push on it with my fingers. I move the piston down, and I want to know what happens to these various forces that exist that previously were all balanced. Okay, so the idea here is we're eventually going to want to imagine pressing this down, and then if I let go, what is the net force on the object? Okay, so hopefully you've had a chance to think about that. Let's talk about these forces in turn. So we have, maybe starting with the force of gravity. If I move the piston down a little bit, well, it's still m times g downward. So the force of gravity doesn't really change. It remains the same. If I think about the force of the outside air on the piston, well, the outside air pressure also doesn't really change if I move the piston down a little bit. And so the force from the outside air, it's still equal to that outside air pressure times the area in a downward direction. So finally, we can think about the force of the gas inside the piston. And in that case, what we expect is that as I move the piston down, so this compresses the gas. We're told that the cylinder is insulated, and so that would mean it's some adiabatic compression of the gas. And so I know then that if I have an adiabatic compression of the gas, that as the volume decreases, the pressure is going to have to increase. We know that P times V to the gamma is equal to a constant. And so as I compress the gas, as we expect, there would be some upward force that would be greater than what we had before. So you're going to feel that increased pressure due to the adiabatic compression. Okay. And so in this case, the answer is A, that as I press the piston down a little bit, then the force from the gas will increase in magnitude a little bit, while the other forces will remain the same. Okay. And so that means if I look at the net force from these three contributions, it's actually in an upward direction if I press the weight downward a little bit. Let's think of the opposite situation. So now take a few minutes to just pause the video and think about the other case where I maybe pull up on the piston a little bit. So I raise it above its normal equilibrium position. What would happen to the various forces in that case? Okay, so if you raise the piston a little bit, then again, the force of gravity isn't going to change. The force of the outside air isn't going to change. And now in this case, we're expanding the gas adiabatically. And so because the volume is going up, we expect that the pressure will go down. And so the force on the gas from the inside is going to be less in magnitude than it was before. And so what that means is if the forces were previously balanced in the equilibrium position, now there's a little bit less upward force from the inside. And so there's going to be a net force in the downward direction. So we've demonstrated in the context of this system the idea of a restoring force. Okay, so a restoring force, it's something that applies to what we call stable equilibrium configurations. Okay, so this is not only are the forces balanced in the equilibrium position, but when we're talking about a stable equilibrium position, what it means is that if I displace the system a little bit away from that equilibrium, then there are some forces that act in the opposite direction to bring it back to the equilibrium position. So that's what we saw for the gas in the cylinder. And this is also true in another very characteristic example where you have a mass attached to a spring. Okay. And so in that case, you're probably used to talking about this in high school. If you compress the spring a little bit, there's an outward force. If you stretch the string, there's a force pulling back. And so that would be another example where you have restoring forces. Okay. Similarly, I have looked around my house for a demo. I couldn't find a spring, but I found this yellow exercise band and this very interesting colored piece of exercise equipment. This is looks like 3-pound weight. And so here's an example, just so you can watch it, where you have various forces. In this case, the force of gravity downward on the purple weight and the force of this yellow exercise band upward. And here we're in some equilibrium position. And now if I move the weight downward a little bit, what happens is that now the force of gravity is the same, but the force of the band is a little bit more because it's stretched out. And so we have this net upward force if I were to take my hand away. And similarly, if I move it up, then the force of gravity is the same, but the force from the yellow exercise band is less. And so if I were to take my hand away, there would be a net downward force. Okay, so that's the basic idea of a restoring force. And this is a very universal phenomenon whenever we have situations where an object is in equilibrium. And most equilibrium situations that we experience are this case of stable equilibrium. The other case, unstable equilibrium, basically means that if you perturb it, if you change it a little bit, then there's a force that takes you away from that situation. And so that's generally not something that that you encounter because it's, as we say, unstable. So any small push on that equilibrium situation, it's like a ball at the very top of a hill. It would roll down. So when we talk about mechanical equilibrium, we're normally talking about stable mechanical equilibrium. Okay, so we've understood that there are these restoring forces. Now what we want to imagine is actually some time-dependent situation where we start out in equilibrium, we displace the system somehow, and we want to see that these restoring forces will in general lead to some oscillations. Okay, and so we can just, of course, demonstrate that. Well, let's just see. Tangled up into the wire here. So let's actually get right up on the chair and have a good oscillation. So first I could imagine displacing it upwards from the equilibrium position. Okay, and then you see there is a nice oscillation going on there. Or similarly, I could start out and stretch the object downward. Okay, so just a little bit, and again, what I find is that it oscillates back and forth for a while around that equilibrium position. So let's try to understand in detail how this oscillation arises based on the idea of restoring forces. So in this situation, we first think about the case where we displace the object down below its equilibrium position, and we imagine that it starts out with zero velocity at that position. So we've understood that in the stable equilibrium situation, there will be restoring forces in the upward direction. And so we have a net force that in this case will cause an acceleration upwards, taking us back towards the equilibrium configuration. So that acceleration, that upwards acceleration, is going to be non-zero as long as we're below the equilibrium position. And so once you get to the equilibrium position, actually you don't just stop there, even though if we just started it there stationary at the equilibrium position, it would just stay there. But in this case, it's been accelerating for a while, and so it will have some velocity upward once it gets to the equilibrium position. And so in that case, it'll carry on past the equilibrium position. And then once it's past the equilibrium position, we're going to have a downward net force. So that's your restoring force acting again. The downward net force will cause a downward acceleration by Newton's second law. And so that upward velocity will decrease and eventually come to zero. At that point, we're still above the equilibrium position. And so we'll have a net downward force because of our restoring forces. We'll continue to have this net downward acceleration. And so now the velocity will start increasing in the downward direction. And we'll come back to our equilibrium position. We'll have some downward velocity at that point, and so we'll just keep going. And so now we're back to the original situation. As that velocity decreases, we'll be back to the situation where you're stationary, but you're down below the equilibrium position. And so you can see then that this cycle would repeat. Okay. And so we've already kind of done the demonstration of that with the exercise band and the purple 3-pound weight. So our next goal is going to be to understand more mathematically how to describe this time dependence, how to describe the displacement as a function of time in these situations where you have restoring forces. Okay. So we always kind of expect this periodic motion, but there's lots of possible periodic functions, and we might be interested in what the specific function of time will look like, and what determines the period of this oscillation, for example, and so detailed quantitative mathematical questions like that. And so we're going to start by understanding something about these restoring forces. We're going to start by thinking about sort of quantitatively, if I change the displacement from 0 to some positive value to some bigger positive value, or to a negative value to a bigger negative value, what does the restoring force look like? How does the magnitude and the direction of the restoring force change? So to be really concrete, I want you to think about this same example that we had before. Think about what happens as I move that piston up or I move it down, and think about what the net force from these 3 contributions would be as a function of this displacement. Okay, so try to make a sketch of the net upward force of the 3 different forces here. Okay. So pause the video. And yeah, definitely take some time to think about this one. Especially think about, does it behave the same way if you compress versus if you increase the volume. So let me go ahead and draw the system again here. And I'm going to draw a graph where this is going to be my delta x, and then this will be my upward force. And so by definition, if delta x equals 0, that's the position where we're at equilibrium. And so we expect that there's going to be no restoring force there. That's the place where the net force is equal to 0. Okay. And what we expect is that if you increase delta x, so you take delta x to be positive, in this case, the idea of a restoring force says that there should be some downward force. And so in terms of our upward force here, this is going to be a negative value as delta x gets positive. And as delta x gets negative, then we should expect positive value. So if you press it down, we should expect the net force to be upward. Okay, so it should be something like this that goes from positive over here to negative over here. But in this case, it's not really a symmetrical situation. And so we might expect that the graph on the left and the right, it might go upward in a different way that it goes downward. Okay, and indeed, we can think in detail about what would happen with these forces. And so let's first think about the situation where you start compressing this. And so one thing you notice is that there's really only so much that you can compress it. So there's this limit for delta x. I mean, at some point, the piston is going to get right to the bottom of the cylinder. And so you can't really go beyond that. What happens when we get close to that limit? Okay, well, we've seen that in adiabatic compression, the pressure tends to go up and the temperature tends to go up quite rapidly as the volume decreases. So specifically, if we look at the fact that P times V to the gamma is constant for adiabatic compression, then we see that as the volume goes down to 0, so as we come right down to the bottom there, well, the pressure actually would according to this formula, just keep going up essentially to infinity. And so according to that, then we would have actually an asymptote here for our upward force, because that inside pressure is just getting larger and larger. It's approaching infinity as we approach 0 volume. What about the other direction? So if I increase the displacement above the equilibrium position, well, in this case, there's no such limit. We could, if our cylinder were infinitely long, we could just keep moving the piston up and up and up. And in this case, again, looking at this formula, we would see that as the volume goes to infinity, well, that inside pressure is just going to go to 0. Okay. And so at that point, as that inside pressure becomes smaller and smaller, it basically is now negligible compared to the other forces. The force of the outside gas and the force of gravity are remaining the same. And so for large values of the displacement, basically we just get to a situation where our upward force is negative, and it's just the contributions of those of gravity and the outside air pressure. And so we kind of expect that we're going to eventually just approach some constant downward force, which is from gravity and the outside air pressure. So you actually expect to have some kind of horizontal asymptote. And so this is kind of characteristic of situations where you have restoring forces. There's not necessarily any kind of symmetry between squishing the object and stretching the object. Okay. And as a result, this can make the oscillations in general fairly complicated when you have kind of arbitrary displacements to start things off. But there is a simplification that occurs, and that comes by looking at the region very close to the origin here. So in other words, if we restrict to the situation where your displacements from equilibrium are very small, then you'll notice that the graph looks a lot simpler. Okay, so what I'm talking about is just zooming in to this part of the graph where we say we're not going to allow the thing to oscillate very much. Okay. So let's have a closer look at that region of the graph. Here I have it on my slide. And basically the observation is that if I do zoom in to that region near the origin, then essentially any function like this that is positive for negative values of x and negative for positive values of x and equal to 0 for 0 values of x, if you zoom in on it, it's going to look like some downward sloping line. And so if we're thinking about a fairly general situation with stable mechanical equilibrium, and then we just consider very small oscillations, small displacements from that equilibrium position, then we can accurately model the restoring forces as being described by a linear function with a negative slope. And so we're familiar with the mathematical description of that. That would just be f equals minus kx, where k is equal to the slope of the line. So for any kind of situation where you have stable mechanical equilibrium, you can figure out some value of k, and that just kind of characterizes how strong those restoring forces are in the vicinity of the equilibrium position. So this kind of thing probably looks familiar to you, f equals minus kx. This is what's known as Hooke's law. And probably in high school, you saw Hooke's law as being applied to a spring, or our model of a spring, this exercise band. Okay, so probably you saw this applied to saying that if you stretch a spring, then there's a force in the opposite direction, which is proportional to the amount of stretching. And similarly, if you compress a spring, maybe not so much for this exercise band, that there's going to be a force which is causing this spring wanting to make the spring go back to its equilibrium length, and that the force is proportional to the stretching in that case as well. Okay, so this is sort of taken to be an exact formula for what we call an ideal spring. But what I want to emphasize here is that it's really a very universally applicable formula as long as you're in a situation perturbing about mechanical equilibrium and you're keeping the displacement small, so you don't, say, get into this regime where it becomes no longer linear. Okay, so that is the thing that we're going to be able to have a lot of control over and understand in great detail, the situation where we have oscillations about the equilibrium position in the sort of range of displacements where Hooke's law applies. Okay, so the remaining discussion, we're just going to assume that to be true. And so we can think that's either true because we're just keeping the displacement small, or because we're talking about some ideal spring system. Okay, so now we get into some actual mechanics, some Newton's laws. We're going to use Newton's laws to actually predict what the time dependence of the displacement is in a situation where you perturb something from mechanical equilibrium. Okay, and so what I want to emphasize, this is just going to be standard F equals ma, but I want to present like the use of Newton's second law. I want to present this F equals ma kind of equation and what it does for you in maybe a different way than you've seen before. So what F equals ma does for us is it allows us to predict the future. And that sounds fairly dramatic, but that's really what physics allows us to do in many situations. We can look at what the current situation is, and then we use the laws of physics to actually predict what will happen in a short amount of time or in a longer amount of time. Okay, and so let's go through how this works in our simple example of, say, a mass on a spring or a mass in a situation where we have restoring forces. Okay, so we just realized that in that situation, if I displace an object, then we're going to have a force which is equal to minus k times the displacement. Newton's second law then tells us that the acceleration, which is equal to the force over the mass, will be equal then to minus this constant k, the slope of our force versus displacement graph, divided by m, which is the mass of our object. And so we have a relation that allows us to determine acceleration based on the displacement of our object. Okay, so how do we use that? And so the thing we can realize is that acceleration is, of course, the change in position over the change in time. I mean, in terms of calculus, it's the derivative of the velocity. Sorry, acceleration, I should have said velocity. It's the change in velocity over the change in time, or the derivative of velocity with respect to time when we define it precisely. And so Newton's second law here then tells us that we know the rate of change of velocity if we know the current position of the object. Okay. So that's one thing. If we know the rate of change of velocity, that means if we know the velocity now, then we could predict the velocity a little bit of time into the future. The other thing we want to predict is how does the position change a little bit of time into the future? And that comes just by using the definition of velocity. Okay, so if we know the velocity, we also know how the position will change going into the future a little bit. So let's have a look at our equations now. Together, Newton's second law plus the definition of velocity, it allows us to take the current position, x, and the current velocity, v, and then it predicts for us the rate at which those things are changing. And so if we say want to know what the new velocity is 0.01 seconds into the future, so say a small amount of time into the future, or what the new position is a small amount of time into the future, well, then we could just multiply those rates, the rate of change of velocity, by that amount of time, and that gives us the change, the amount by which velocity changes. Okay, or we multiply the velocity by the small amount of time, that gives you the amount by which position changes. Okay, so we started with some position, some velocity, and then we were able to predict, based on these rates of change, what those positions and velocity would be a little bit into the future. And now we could just repeat that. So we can keep predicting the rate of change of velocity and position based on the current velocity and position. And those rates of change will allow us to figure out the new velocity and the new position a little bit of time into the future. Okay. So mathematically, this set of equations is what we call a system of differential equations, of ordinary differential equations. You'll see lots of techniques for solving these things in a future course. But all I want you to be sort of convinced of now is what I said, that these equations are in principle enough to determine the future evolution of the system. Okay. So what we're going to do is, what I will do for you is actually just give you the solution of these equations. And then you can check that this solution satisfies the equations. And I'm also going to give you a solution which is general enough to apply for any initial x and for any initial velocity. Okay, so basically, I'll give you this mathematical function of time. So x of t equals a, and then the sinusoidal function of time. And then what I claim is that by choosing this number a here, and by choosing the number phi here, I can get any initial position and any initial velocity I want. So we're going to see this in much more detail next class. For now, we can just kind of check that taking this function and then first calculating the time derivative to determine the velocity, and then calculating the time derivative of that velocity function, you can check that it satisfies these equations. And it satisfies the equations if you choose this parameter omega, it's the Greek letter omega, which if you choose the parameter omega to be equal to the square root of k divided by m. Okay. Great. So actually, let's try to understand, what we've learned here. So just to summarize, we wanted to understand how the displacement will look as a function of time. What we did was we first understood what the forces were as a function of displacement, and then we used Newton's laws to understand how those forces will lead to a changing velocity. Okay, and we know that the velocity tells us how the position changes. What I'm claiming is that if you solve these equations, then the general solution turns out to be this one. And it's easy for you to check that solution just by taking these derivatives and then evaluating and seeing that the left and right-hand side of this top equation is going to be equal. Okay. So you probably all know what a cosine function looks like. It's characterized by a few different parameters. We have the amplitude of the cosine. That's going to be how far do you get displaced from equilibrium at the maximum. And then another very important parameter is the period, which is how often does this repeat? Just the amount of time from, say, when the object is at the top of the oscillation to the next time when the object is at the top of the oscillation. Okay. And these parameters are related to parameters in this function. So the amplitude is just the constant out in front. And then we'll understand the relation. There's a slightly more complicated relation between the period and this parameter omega. Okay, so these two things are related to each other. And then the final parameter, this phase, we'll see next time. It has to do with where do you start your oscillation. So if I change this phase, this just shifts the graph to the left or to the right. And so if I started the oscillation at the top, I might use one phase. If I started it at the bottom, I might use a different phase. So let's end here with a couple of questions just to get you thinking about the relation between the cosine functions that we use to describe these oscillations and some graph that we might make of the actual motion of the object. Okay. By the way, I didn't mention the words simple harmonic motion. That's kind of the jargon that we use for these oscillations about an equilibrium position when you have the linear restoring forces. So simple harmonic motion is this motion where the position as a function of time is a perfect cosine or a perfect sine function. Okay, so here's an example of a graph of position versus time for an object that maybe was released at a position above the equilibrium position. And so we have a downward oscillation and then it comes back up and then it goes down again. And what I've told you is that these kinds of oscillations are going to be described by this particular function for some choices of the parameters. And so what I want you to do in this question is just figure out from the graph, what is the amplitude of this oscillation and what is the period of the oscillation. And then if you have extra time, see if you can figure out what this omega parameter is in the cosine function. Okay, so let's do that. Hopefully you've had a chance to think about it. And so this one is pretty straightforward, I think. So what you notice is that the maximum value of this function, according to the graph on the screen, is 1 centimeter. That is the largest that this ever gets. And the minimum is -1 centimeter. And so this will be true if the parameter a in front of the cosine, okay, that is, which is our definition of the amplitude, is just equal to 1 centimeter. Okay? Because you know that the biggest that cosine ever gets is 1. And so the biggest this function x of t will get if you choose a equals 1 centimeter will be 1 centimeter. And it'll oscillate between 1 centimeter and -1 centimeter. And so we can conclude that that must be the parameter a. Okay. So that's the first part. The next part is what is the period of this simple harmonic motion? And again, this is very simple. It is just the amount of time that it takes for us to go from the configuration where it's at the top to the next time where it's at the top. And we can look from the graph to see that that takes 4 seconds. So for this one, the period is 4 seconds and the amplitude is 1 centimeter. Okay, so actually let's go ahead and try to understand what is the omega parameter in this cosine function. And so I'll have you think about that by using the following clicker question. So again, take a moment to understand. Let me just point one thing out. This phase, in this case, I've set it to 0 in the next question, because we know that when you have a regular cosine function, it does start at 1 and then decreases. And so if I set this phi to 0, then our function will have that property. Changing phi, as we'll see next time, corresponds to shifting the function left or right. Okay, so here we see that the phase is set to 0, and we have the amplitude set to 1, and we have various choices for the parameter omega in the oscillation. Okay, so let's try to understand which one of these is the right answer. Okay, so we know that the period is 4 seconds. And so we should get that x, if you plug in 4 seconds, is equal to 1. And that should be the first time that the cosine goes back to 1 after the time t equals 0. So all of these functions are 1 at time t equals 0. And we're just basically going to look at what is the next time when the function goes back to 1. And that will happen the next time that this function goes back to 1 will be the time when, so let's look at the function cos of omega t. So all of these can be written like that. Okay. So the next time that this function goes to 1 is going to be the time when omega t is equal to 2 pi. Okay. And so that time is equal to 2 pi divided by omega. And in our present example, what we want is that time to be 4 seconds. And so what we can say is that 4 seconds is equal to 2 pi divided by omega. And so omega is going to be equal to pi over 2 inverse seconds. So comparing with the answers here, then we see that the answer is E, that x of t is cos pi over 2 times the t. Okay. So that's basically all for today. Just to summarize what we just found in that last question, we understood that the period is related to the omega parameter by this relation t equals 2 pi divided by omega, because you can see that if I plug in little t equals 2 pi over omega, well, then that means that, so compared with t equals 0, what's inside the cosine function increases by 2 pi. Okay, so that's a number which is we call the angular frequency. It's closely related to the usual concept of frequency. Usual concept of frequency would just be 1 over the period. And so you see that because omega is 2 pi over the period, it's just something that's related to f by multiplying by 2 pi. So you'll see this. This is just sort of a jargon that's used when we're talking about sines and cosines. The angular frequency is just the number that appears in front of time. It's related to the regular frequency by just multiplying by 2 pi. And it's related to the period by that result. Okay. So we'll have lots more examples in tutorial and next class to help you understand all of this mathematics of oscillations. We'll see you next time.